In this final video involving Newton's second law, we're going to change up the situation a little bit. Now imagine that the crate man chooses to push down on the crate instead of pulling on the rope. He pushes down with the same force as before, but down and forward at an angle of 32 degrees to the horizontal. The weight of the crate and the coefficient of kinetic friction between the crate and the floor remain the same. And now we ask, this time, how much force must the man exert to move the crate at a constant velocity? Well, the first step in the problem-solving process is always to draw a diagram showing all the forces acting on the object. When we do that this time, we see that the diagram is a little bit different. Instead of having a tension force going up and to the right, we now have an applied force going down and to the right. Other than that, however, the other three forces, the weight force down, the normal force up, and the friction force opposing motion, remain the same. Step 2 is to establish a coordinate system, and that remains the same as well. There's no compelling reason to change it. The x direction is still horizontal, and we will still call to the right positive because the way we've drawn it here, that is the direction the crate's going to go. And we will still call the y direction vertical with up being positive, just sort of arbitrarily, because the crate is still not going to move up or down. The third step now is, given the coordinate system that we have, do any forces need to be broken up into components? Well, the answer is yes. The applied force must be broken up into two components, which we will call Fay and Fax. Note the difference, however, in that the y component this time is downward instead of upward. The x component is still to the right. Now we use the trigonometric functions to write out formulas for those components. You see that the process is the same that we've gone through in every video. There is no change because the y component is still opposite the 32-degree angle and the x component is still adjacent to the 32-degree angle. So nothing really changes here. The formulas we have here are similar to the formulas we had before. Then, of course, step 4 is use Newton's second law to figure out what the question's asking you for. In this case, we are once again moving the crate at a constant velocity. So that means that our acceleration in the x direction is going to be 0. The crate is moving. It will be moving to the right, but it will not be changing its velocity. It will not be accelerating. So the x acceleration is 0, and the y acceleration is still 0 because the crate is not moving up or down. So here we have a situation of dynamic equilibrium. We write out Newton's second law, as we have done before, as two equations. One equation for the x forces and another equation for the y forces. Looking at our diagram, we see that there are two forces in the x direction. The x component of the applied force, which is positive to the right, and the force of kinetic friction, which is negative to the left. So Fay is going to be positive, the friction force is going to be negative, and because we're moving at constant velocity, that acceleration is going to be 0. This gives us the situation where Fax, also known as Fa cosine 32, minus mu k times Fn is going to equal 0. Once again, we're in a situation where if we want to figure out the friction force, we must first figure out the normal force. And we do that the same way we have been doing it, by turning to the y forces, realizing that the y forces are in equilibrium. The acceleration in the y direction is going to be 0. So the y forces balance. There are 3 of these forces. But notice the difference from our previous examples. Here we have the normal force upward, positive. We have the weight force downward, negative, that remains the same. But here, the y component of our applied force is downward, and so it is going to be a negative force. They must balance, and so solving for the normal force, we get mg plus Fa sine 32. So a little different here. The normal force is greater than the previous example because we have a plus sign there, because we are pressing down on the crate. That causes the crate to press down onto the floor, and that's going to make the normal force from the floor even greater. We'll see that that will now carry over to the friction force as we make the substitution for the normal force. That plus sign is now there. Once again, we take the coefficient of kinetic friction and multiply by both terms in parentheses, getting us this result. We multiply mu k times mg, and we also multiply negative mu k times Fa sine 32 degrees. Notice how both of them have negative signs. Following the same process as we did last time, we take this over to this side of the equation to make it positive, because our goal is to solve for the applied force. And so we have Fa cosine 32 degrees minus mu k Fa sine 32 degrees equals mu k times mg. So now we are in a position to start plugging in numbers and doing calculations. The cosine of 32 is 0.848. The coefficient of kinetic friction is still 0.417, as in the previous example. So that's what we put in there. The sine of 32 is still 0.5299. And the weight is still 1150 newtons. Multiplying these two together and then subtracting the result from 0.848 gets us 0.627 times the applied force equals this right here, which is, as before, 479.6. This gives us an applied force of 765 newtons. Notice that this applied force is much greater than the 448 newtons we had to apply when we were pulling upward. Remember, this is because when we press downward, there is now a downward component to our applied force. That downward component to the applied force results in an increased normal force from the floor, which then is an increased friction force from the floor. And so pressing down on the box to move it requires more force than pulling up on the box to move it.